So, we have looked at the action of some of the prosthetic feet, some of the different designs. Today I brought some to show you actual models. So, this is the Pathfinder 2 foot that you see here. This is a foot that is used for users who perform, users with high activity levels. So, this is the shock absorber at the heel, which is customizable. You can see the valve here that they can just put a pump, or they can either pump it up if they want to say go for a run, or and then bring it back down the pressure if they want to just walk. So, depending on, so that way they can customize the resistance of the foot. So, this is a low profile version. So, it does not have the adjustability. So, it is directly attached to the socket. So, it does not have that alignment which you saw in the picture here. Okay. So, this does not have this dovetail alignment. So, this is and you can see these springs. What happens is when the heel compresses, okay, these springs are deformed also, right, and so that's, so the springs are always trying to come back to their original position, and so, and then as you move, as you go over the toe, they get compressed further, and the release helps in the forward propulsion of the foot. So, you can take a look at these models. These are also for people who can who are moderately active. So, they have these, you can see it has a keel which has the pyramid attachment, and then you have these carbon epoxy plates, composite, made of composite materials. So, these are, because they are very lightweight. So, you will see a lot of composites used in prosthetic components because of their high strength to weight ratio, okay, as compared to metals. Even in metals you will see a lot of aluminum and titanium used. Titanium is used in the high end prosthesis because it is obviously a lot more expensive, but you will see use of a lot of aluminum and composite materials in prosthetic components. So, again these they would, depending on the, so they will have these available in different stiffnesses depending on the activity level of the user. So, the prosthetist will prescribe a certain and will order a certain stiffness for the toe, and the heel of course would be like some kind of a, this does not have it here, but oh, of course this is the single axis foot I was telling you about, this right here. Okay. This is this here is the ankle, the bolt that functions as the ankle, and you have this part at the top which has the pyramid, and you have two bumpers here, like I said, which will control the, so as it compresses, the dorsiflexion and plantar flexion are controlled, and again that is customizable. So, customization is a very important aspect of any assistive device design, because just as even so called able bodied people are, there are vast differences among us. Similarly, when you have an impairment, there could be significant differences in the, say, the level of the impairment, the ability that is available after the impairment, any other secondary problems the person may have, etc. So, the ability to customize, and of course, the weight and height and those, the basic parameters that differs among all of us. So, many of these designs you will see are very customizable. So, if one does not work, okay, you can, there is a bolt here, you can unscrew that bolt, replace. So, the feet will usually come with maybe sets of bumpers. So, you can actually, they may give it to you in 3 different stiffnesses. So, you can actually play around with and find the one that is most suitable for the user who is trying that foot. So, this is a size 10, US size 10, 25 centimeters. So, they mark that on the base of the foot, and you can see here that if I place this flat, there is a slight heel, okay, because it is meant to be worn in a shoe. So, when you wear it in the shoe, then this is level. Okay. So, that these will go into, again these will go into some kind of a foam cover like that. Again you can see that this will be, it will come with the foot shell, or the foot casing will come with a heel height. So, that is but yeah, you are right, if the base plate was flat, then there is no point in having the split springs. Okay. So, this one does not have that ability. So, this one, the heel shock absorption is only by means of the spring itself. So, these are all different. This is a multi-axial foot, the MA stands for multi-axial. So, you could have, it has an ankle which provides motion in both planes, possibly some rotation also about the longitudinal axis. So, moving on, just to recap role of a lower limb prosthesis, because the feet is something that is common to all lower limb prosthesis. So, now we have studied the prosthetic foot in some level of, we have looked at the different designs. And why do we need so many different designs? Why is it, why can't we just have one foot that works for everyone? I mean, human foot, there is only one design, right? It is not like each of us can get it customized. Is that the reason we, no, my question is, why do we have these different kinds of different designs? Why do we have so many different designs? Simple answer is, different people approach a problem differently, come up with different solutions. Okay. The other reason is, if you look at the variation in cost, okay, you can have feet that range from say 1,000 rupees to a few lakhs, vast difference in cost, and therefore, there could also be difference in functionality to some extent, not necessarily, there is nothing that says that you have to always choose something that is most appropriate for the user, and the answer is not always the high end foot. Okay. But one of the reasons they exist is, so if you look at every company that makes these prosthetic feet, they will have a variety of products to cater to different segments of the market. It could be, so if an old lady just wants to walk around the house, okay, after her amputation, she does not need a foot like the Pathfinder, it is not necessary. Whereas a young girl who has lost her leg may be able to do more things with this kind of a foot. The old lady may just need something to ambulate around the house and maintain her independence. So, a foot that still gives her the ability, so she may not need to walk fast, or so a satch foot may be fine, or a single axis foot may be fine for such a person. So, they have to evaluate the cost versus the functional benefits that will be gained by the user, and whether the foot itself is appropriate for the user. Okay, because the most expensive need not always be the best solution for that particular person. Okay. But companies like to have an array of options available, just as all cars get you from point A to point B, right, but you have From the Nano you have Audis and BMWs and Porsches and whatnot, right. So, it is a matter of the market segment that you are targeting and also what the user wants to get out of that. In terms of cars, it is probably just a feeling of, oh okay, it is a status symbol. If you are really looking at a high end car, you are still in the same traffic, right. You are not going to get there any faster, but you are probably slightly more comfortable inside while you are waiting for the traffic to subside. So it is a personal choice, and businesses like to offer their customers that choice to go from. Of course, with devices that are functional, which provide function like this, that becomes even more important in order to accommodate the needs of different types of users. So, now as we move up the prosthesis, so we have looked at the foot, we have looked at some types of ankle joints. Okay. So, we have had the solid ankle and basically flexibility coming from the foot itself, then of course, the single axis, multi-axial, etc., which try to emulate the human foot. Again reviewing, so providing stability during standing and walking, shock absorption. So, if you move up to a prosthetic knee, okay, so a person with an above knee amputation, now the knee also has to play a part in many of these functions. Okay. So, stability in, yes, you need a stable foot, but now you also need the knee also, that becomes another variable. Okay. Another since there is another degree of freedom at the knee, that becomes critical. Shock absorption, maybe if the foot provides some shock absorption, it may be enough. In some cases it may be beneficial to provide some shock absorption at the knee also. Ability to sit comfortably, this is very much the knee, right. Enable forward motion of leg, again in the case of the foot, the especially with the ones, most of these do not have an active ankle. So, you really do not have the active dorsiflexion during swing to clear the ground. Okay. So, these passive feet can't really provide that. Yeah, in some cases they may have like a spring loaded thing that once there is no load on the foot, there may be a way to, I have seen that more in orthosis than prosthesis. But so there may be some compensation the person is using in their gait in order to make sure that they clear the ground. So, they may flex the knee, hip and knee more, for instance, to clear the ground. So, but in the case of the knee, that becomes critical. Assistant push off, of course, is more of the function of the foot. Control pendular swing of the shank is a function of the knee. So, if you look at this is foot and knee, stability in standing and walking. Shock absorption may be foot and knee. Ability to sit comfortably, knee. Forward motion, knee. Assistant push off is more of the foot. Pendular swing, knee. Adjust to different walking speeds. So, how the leg swings, okay, and whether it is ready for the next step. Okay. Being able to control that swing is, if you had the same swing, same resistance to the swing, then you are not going to be able to change your walking speed, because the foot will not be ready for the next step or it is there too early. Okay. So, that is again a function that the knee has to provide. Reduce effort needed to walk, both, it depends on the function of the knee and of course, the function of the foot, the propulsion that it provides, the energy storing and release feet do that. And of course, these apply to both of all the components. Of course, there are other ways also. In some you can have separate components, because we have the endoskeletal prosthesis. Some prostheses actually have a separate component for just shock absorption. So, they would put it, you can have like a shock absorbing pylon. The pylon can actually be something that is like a telescopic pylon that offers resistance, which prevents the shocks from being transmitted, like a suspension in a vehicle. So, the pylon can actually do that. So, you may also have other for sitting comfortably. So, if you want to sit cross legged, for instance, you may have a component that helps to rotate the entire prosthesis. You can have a rotator that is attached to, and that is the advantage of this kind of an endoskeletal prosthesis. You can build up with all these different components. So, you can have a separate rotator which you can use only when you want to sit cross legged, because the advantage of kind of separating out some of these functions is it makes it easier to build the system, because if you have too many degrees of freedom in one, then controlling it becomes difficult. Okay. But for rotation, for instance, usually using a rotator like that is simple, because you use it only when you need to, and if somebody does not need that functionality, if they are not going to sit that way, then it is something that they do not need in their prosthesis, because maintenance is another key. With all these parts put together, if somebody has to keep going back for maintenance of the prosthesis, it can be very disruptive to their normal life. Imagine if you had to keep going and lubricating your joints, or having to get some maintenance done on your body. So, it is the same thing. This becomes a part of their everyday life, and so you want to minimize the disruption. So, designing parts that are low maintenance is key, and one of the ways to do that is to kind of separate out some of these functions, so that you only provide what is absolutely necessary. So, if you look at the gait of someone who has either lost part of the leg above the knee, so has had a transfemoral amputation, or if they have muscle weakness and they can't control the knee. Okay. I showed you the KAFO, the knee ankle foot orthosis, which is used for people who have muscle weakness or some other kind of. So, a KAFO is typically prescribed for somebody who has, say, a quadriceps, they can't control the knee. Okay. So, you have these braces which basically take the load, and what we do there is have a locked knee. So, the KFO with a locked knee, essentially, so the knee stays locked. So, then there is no worry about stability. Okay. The person can't control the knee with their and in many cases for prosthesis also, they tend to use that kind of a locked knee. So, here is an example. This is the most common type of locked knee that is used. It is called a Droplock. Okay. So, if I do this, then it unlocks, and the user can unlock it only for sitting down. Once they straighten the leg, ideally it should drop down like that and lock, so that they are now ready to stand or walk with stability. So, this is a very simple solution. You can see that the knee is essentially just a hinge. Okay. So, this is an orthosis where you have these drop locks, and the knee is essentially a hinge, and it provides stability. So, it is the simplest solution to provide stability. Now, a person who is using this, and it is sometimes used in prosthesis also. So, if a person in an above knee prosthesis, if the person has limited control over their residual limb, or if they tend to walk on uneven terrain where maintaining balance becomes difficult, then they may be prescribed. It is also one of the least expensive, it is just a bolt, right. In this case, for a prosthesis it would just be a bolt. They would prescribe a knee like that with just locks, and the only reason they provide unlocking is for sitting down, because if you did not have the unlocking, then you can't sit down, you have to have an extended leg all the time. Okay. So, they provide the unlocking mechanism only for sitting down, and otherwise the knee stays locked. So, yes, it fulfills the purpose of providing stability while standing and walking. Now, how does the person have to, how will the person have to walk with such a knee? They will have to figure out some way to clear the ground. So, now you do not have a separate swinging shank, and you do not have any. So, the most common that you will see type of walking that you will see is circumduction. So, from the hip, which is where they have control, they will move the leg in this kind of along an arc. You have both abduction, flexion, extension at the hip to move the limb in circumduction. The problem with this kind of walking is that there is research that has shown, okay, not only is the gait noticeably abnormal, okay, it is very noticeably abnormal when somebody walks like that, it also leads to increased energy expenditure. It's difficult to walk like that, and so in many cases the user will reject the prosthesis after a while, because they just find it to see this is quite heavy. They already have either limited musculature or weak, very weak musculature. So, operating a device like this with their own power becomes very tiresome, and so in many cases they would stop using a device like that, but it at least enables them to still walk. Okay. And there is also research that has shown that because of this abnormal gait, it causes damage to other joints in the long run. So, if you look at the kinematics and the force plate data and try to do the inverse dynamics for a person with this kind of a gait, you will find like that the hip loading, knee loading on the other side, everything is higher than what it is for a person with a so called normal gait. Okay. So, this is another disadvantage of this kind of a locked knee, but in many places because of economics and because of lack of accessible surroundings, environments, or uneven terrain, in many places they end up getting, like in India and other places, people who are economically disadvantaged end up getting a prosthesis like this. So, this is, so some people may still need to use a locked knee in this kind of an orthosis. So, if you see, this can sometimes be very cumbersome to operate. This Droplock is very simple, but what happens is sometimes, so they may be wearing, many people wear this orthosis under their clothes. So, if they try to unlock this, then it may get stuck in their clothing, which can also be a safety issue, because when they stand up, suppose it gets stuck and does not lock, then they are going to fall down. And you can also see that the design has such sharp edges. Okay. So, many of them experience tearing of clothes and all that. These are small things that can be fixed fairly easily. So, one of my students has come up with a design that is a lever operated, it is a user friendly alternative to this Droplock, and what it does is there is a lever here. Okay. So, the person can operate it and it is spring loaded. Okay. So, the lock itself is spring loaded. So, the person can operate it discreetly, okay, and they only need to operate one side of it. Okay. So, they do not have to bend down to lift that. So, they operate it, it will bend, they can sit down, and you can see it is made with nicer contours. Also it provides more flexion, again the Maruti car scenario I was telling you, because it is very difficult. Those things provide only maybe 90-95 degrees of flexion, which makes it very difficult to sit in cramped spaces, or like even in the desks that you are sitting, okay, they are pretty narrow. So, it is difficult to sit in cramped spaces, and so this provides increased knee flexion, and you can see that it positively locks because it is spring loaded. So, when it goes up to the extension position, you can hear that click. Okay. So, it positively locks when it goes to the extended position. So, this is one of the designs that we are working on in our lab, and we will be starting the user testing with this. We have already started it in some places and hope to have this available on a larger scale, because it, especially for, if you imagine if somebody had to wear an orthosis like this on both sides, bilateral, okay, if they are wearing a bilateral, then for them while sitting down they will bend down, try to unlock one side. When they try to do the other side, sometimes one of these will drop down, the drop lock will come down. So, it becomes a very difficult thing for them to do. And also, like when you are in public transport and all that, you may not have that kind of space to bend down, unlock, and use these kind of devices. So, the idea is to make the operation more user friendly and discreet. Still, biomechanically this is not the best solution for walking, but some people may need it because they may not have the muscle strength for walking otherwise. Okay. So, there may be some candidates who still need only this kind of a solution. So, if you look at a prosthetic knee, overall we need to compensate for missing muscles and normal control mechanisms that are there in the body. So, if you break it down to the walking cycle, then in the stance phase you need weight bearing stability, and typically that is achieved by some kind of a braking mechanism in the knee. They will have some kind of a brake, so that when there is load on the knee, it is difficult to flex it. Okay. Geometric stability, we will talk about that in a little bit more detail, that is using some linkages that will provide stability. The advantage of geometric stability versus a braking mechanism is, a braking mechanism wears with time. Okay. So, a person may actually become dependent on the braking mechanism, and then suddenly one day it may have worn off to the point where it is not able to brake anymore. Okay. So, whereas a geometric stability, it arises out of the geometry of the linkage itself, and so it is not subject to wear with, it does not change with time. So, it is more consistent. Then the more sophisticated designs have some kind of microprocessor control that is built into the knee, which will sense what is the load on the leg, and then accordingly make sure whether whether the knee can bend or not, whether the knee has to be kept stable, or it will look at, so it will have some kind of a control system to determine that. So, stability in the stance phase, which is very critical for walking, is provided by some of these different mechanisms. In the case of swing phase control, one of the requirements is to accommodate different walking speeds, okay, and basically assist the extension of the shank. So, if gravity, with the human leg, human shank, you have a certain mass and moment of inertia. Okay. Most of these prosthetic legs are lighter, because to improve the overall efficiency of walking, the mass is reduced, and because of the lack of the other control mechanisms. But that can also hinder the extension of the shank. Okay, it may not be enough. So, you may actually need something to pull it, pull it forward. Gravity alone may not be enough to assist the extension of this shank. The other aspect of swing phase control is to provide toe clearance in some way. Okay. Ensure that toe clearance is provided. In addition to that, if you look at shock absorption, what you have in the foot may be enough, but if not, if you look at normal walking, if you want normal gait, you remember it at the knee you have two instances of flexion. You have, so if you look at the knee flexion versus percentage of gait cycle, the knee pattern looks like this, right, over the gait cycle. So, this is the knee flexion 0 to 100% of gait cycle. You have some flexion in the stance phase, and that contributes to the shock absorption. Now, in many cases this knee flexion is difficult to provide in a prosthetic knee, because again it is this happens during stance when there is loading on the knee. So, if a person has loaded the leg and they start feeling, they find the knee is bending, it gives them a feeling of insecurity. Okay. So, they may not be able to handle that. They may prefer to feel that, okay, my knee is locked, I can bear weight on it, rather than a slight stance flexion. Also, controlling that stance flexion is important. Even if you provide, so say you provide a new amputee with a knee that allows some kind of, so they are not used to a completely locked knee during stance. So, they may be more open to be trained with a knee that provides stance flexion. Controlling the stance flexion is also an important aspect in the design, because if it's if you have free flexion, then again stability becomes an issue. The other instance where you need some kind of dampening or shock absorption is when the leg swings forward, okay, and then contacts the extension stop, okay, because you do not have any eccentric muscle action decelerating that, okay, helping to. So, when it contacts that stop, otherwise you will have an impact. Okay. So, that is another instance where there needs to be some kind of dampening in the knee. So, there are various types, again as with the prosthetic feet, the kinds of knees that are available, many. You can have single axis knees, and these can have different types of single, swing control. Okay. So, swing control can be, you can have friction, you can have swing control using hydraulic or pneumatic units, or now you also have knees that use MR fluid to control the swing phase. Then of these, some of them can be just mechanical, hydraulic or pneumatic, or they could be also microprocessor control. They could be some level of microprocessor control inbuilt into the knee to handle different situations. So, you could have, here is an example of, so the simplest single axis knee is basically just a bolt, okay, and it will have like a sleeve bearing around it, okay, and if you tighten that, the sleeve of that bearing, so it could have like a slot, the spin will be in a casing which has like a slot, just similar to this tube adapter that I showed you, and if you tighten this, okay, this kind of, if you have a slot and you tighten a bolt, then it is going to increase the friction against that pin, against the knee bolt. Okay. So, the simplest type of single axis knee, free moving single axis knee, has frictional swing control. So, this is simplest, simple, it is inexpensive. The downside of frictional swing control is you can adjust the friction for a particular walking speed. If you change your walking speed, you have to go back and adjust the friction. It only works for that particular, it does not adapt on the fly. It does not, because the friction is not velocity dependent, right. On the other hand, if you have a hydraulic or a pneumatic unit, the behavior of the, it will push the fluid. So, you will have a piston cylinder arrangement, you could have it with a single axis knee, and as the knee bends or extends, you have this piston moving inside the cylinder attached. In those cases, because that movement is velocity dependent, the hydraulic unit can easily adapt to different walking speeds. So, even if you set it for one walking speed, there is a range around that walking speed for which it will be able to still function appropriately. Again, added weight, added cost, added sophistication, added maintenance requirements, because you could have leakage, you could have other issues with that. Okay. So, the simplest was the lock, then you have the single axis with friction control, then you have single axis with more sophisticated swing control. This is a knee that is a slightly different version of a single axis knee, it is called the stabilized knee, and if you see, this is the knee bolt. Okay. And it has this casing which has a slot in it around the, so you can adjust the friction. So, there will be a bolt that connects these two across the slot, so that you can tighten that and squeeze the knee bolt accordingly to change the friction response of that bolt. In addition, what this also does is, there is another pivot here, and to which this is, and when you load the knee, that further squeezes that slot, and the idea is that when it is load bearing, it will lock the knee. It uses only friction, okay. It uses only friction, but it tries to do it in this manner, it tries to. So, it used to be called, the very first design that was similar to this used to be called the safety knee. They said, if you walk with this, you are not going to fall because it will lock. But again, the problem is with a mechanical braking system like this. This is essentially, when it is loaded, it acts like a brake system, things wear, and so, people started suing them, saying, you said it is the safety knee and I still fell walking with it. So, that is one of the stories behind this knee. So, they changed the name to a stabilized knee rather than a safety knee. So, here you see, what you see here is, so you have this collar, okay, which will go on the pylon, and then you have a spring, okay, and then you have another movable collar at the bottom, and these two are attached to the two sides of this knee. So, as you bend the knee, this moves up, this slides up the pylon and compresses this spring. Okay. So, the view of this, the spring, see, the knee should actually be facing me like this. Here I am looking at a sagittal view of the knee, okay, but an frontal view of the extension assist. Okay, so it is a bit confusing. Imagine that the knee is turned around, so it is facing you, and these loops go around this on that side, and on the back side the other loop goes around that. Then as the knee flexes, so imagine there is a spring that, okay. So imagine there is a spring on this part which compresses as the knee bends, because it is attached to that string, right. So it compresses, and then so as the knee extends, it is going to provide an extension assist. So this is a simple design for a mechanical extension assist for the knee. So to help the knee in, because it stores the spring energy and then releases it when there is no load, or as the knee is straightening, it will help the knee straighten. This geometrically, this is a knee that provides the geometric locking that I was talking about, and we will explore that more in the coming classes. Okay. So you have a braking type of a knee, and then this is a knee that has a hydraulic control. Okay. So this is a knee that has again, so this is the piston cylinder arrangement I told you. You still have a single axis knee, but as the knee bends, the piston gets compressed, and there may also be a spring or something to help it extend. So you can control both the flexion and the extension resistance on this knee. The C-leg is a sophisticated microprocessor control knee, and we will, you can see again they come in a variety of colors and geometries and different price ranges. Knees can cost anywhere up to $100,000. $100,000. So, that C leg, that not this one, the C leg can run $30,000 to $100,000. These microprocessor control knees can be pretty expensive. So it is out of range for most people, even in Western countries. That is one of the sad parts of some of these developments, is that scientifically yes, it is very sophisticated, but unless you can bring the cost down, your ability to make an impact in the lives of the people who need these kind of devices is limited.